Now we will consider a simplification in this general result for energy balance during crack propagation. That was a general result, and I'm going to introduce a simplification regarding this. And this is generally referred to as Griffith Theory for crack propagation or fracture. And this is applicable for a brittle material, for an ideally brittle material, the energy dissipated in plastic deformation. Plastic deformation is negligible and then which term can be here eliminated from this equation? As results shown here, material is assumed to be an ideally brittle material. And which term can you consider here, or which can be equated to zero, in other words? That's right, UP. It's associated with plasticity, and we are now able to rewrite this equation. The original one is shown here. For an ideally brittle material, this is zero. I'm going to move this to the left side and rewrite this equation. And the final result is the WdA minus dUE dA equals the gamma dA. That is a condition for fracture or crack propagation in a brittle material. Or let G, any quantity, is defined be equal to dDA W minus UE. And G is known or defined as energy release rate. This is defined as energy release rate. It's a measure of energy available for fracture per unit of newly created fracture surface. Or G is a measure of the energy available during fracture per unit of newly created crack surface area. And this is the driving force for fracture, G energy rate, and it's used as a parameter in fracture mechanics. That's the left side of this equation. On the left side is G, and the right side, on the right side we have the gamma dA, and it's generally referred to as resistance to fracture. To fracture. And you can express the gamma dA, for example, if lowercase gamma is the energy required to form a unit of new material surface, and if gamma is constant, it's independent of crack length or propagation, can express delta gamma required for crack propagation as total crack surface area, extension in the total crack surface area, which is 2 delta A, and multiply this by gamma to find the energy required. Therefore, delta gamma over delta A. Now, this is a constant, it's 2 gamma. And this is equivalent to the gamma dA, or this is equivalent to the limit delta A goes to 0, delta gamma over delta A, which is the gamma dA. This derivative can be replaced by this constant. The gamma dA is replaced by 2 gamma, or R. Can write the resistance of the material to fracture as 2 gamma. And primarily, there are 2 terms here. The driving force or energy available for fracture per unit crack surface area. And this is G. And the other one is a material property, shows the resistance of the material to fracture, the energy supplied for crack that needs to be supplied for crack propagation. And a fracture criterion is actually derived in terms of energy quantities. We have derived a fracture criterion. And this is G equals R. This is our fracture criteria. G is energy release rate, and the units used for these, the general units used for these quantities, it should be energy divided by square of area, or joules per meter squared. That's the unit. SI unit for these quantities. Now, we have to evaluate these, and we will see how we can evaluate these quantities. There's, for a general structure, you can be given an arbitrary structure. And the question is, how are you going to evaluate G? And that is known DDA W minus QE. This is G. And this can be found through mathematical analysis. It depends on crack length, loading, material properties, it's a fracture parameter similar to the stress intensity factor, actually. Therefore, this can be used as a fracture parameter. R, the gamma D8 is the material property. It can be measured, testing, and certain factors will affect R, such as temperature, thickness, etc. But these are related. This is related, as we will see later. This is related to stress intensity factor. We can show that energy use rate is related to the stress intensity factor, and R is related to which quantity? It's related to fracture toughness. And this equation, G equals R, is actually the basis of K1 equals KC. If you can show the relations between G and K1 and R and KC, you'll be able to show that this fracture criterion, K1 equals KC, has a sound physical basis, and it's based on conservation of energy principle in general. It's possible to use either G or K1 in actual analysis, but first we have to have an understanding regarding the computation of G. Therefore, we will talk about calculation of energy result we will consider certain general geometries. First, start with a specimen. Suppose that we have a certain specimen, fracture toughness specimen, with a crack. That's the specimen, and we are applying forces here at the ends. This force is F. And load point displacements are going to be defined. Displacement of this point is V over 2. And displacement of the other point, this is also V over 2. For total displacement of the specimen is V. And now crack length is A because this is an edge crack, as you see here. What's the mode of loading? Mode 1, that's right. That's the thickness or the side view of this specimen. Now, crack area, A, is A times B. That's the crack area. And total displacement, V, total displacement of the specimen is V. I'm going to write this as a linear elastic body as C times F. And what is C called here? What is C? It's called compliance of the specimen. It's a linear elastic body. Strain energy stored due to this loading is equivalent to work done by the forces and what's the work done by the forces, or how can I find total strain energy for a loading of F? Now, strain energy is UE. I know the definition of work, integral F times dV over 2. This is the work done by one of the forces. FDU, for example, general definition of work. There are two of these forces, right? Only these two forces do work on the specimen. And multiply this by 0 to V. And contribution to work. Therefore, this is multiplied by 2. So I can write work done as 0 to V FTV. And V is replaced. Total V is C times F. Therefore, F is replaced as V over C times dV, or strain energy is V squared over 2C. I'm going to write it as 1 over 2 V over C times V. And strain energy is 1 over 2 F times V. That's the total displacement. That's how we can evaluate strain energy for this specimen under this loading. I can use or show it on a simple diagram like this. F versus total displacement diagram, and the area is equal to what? And what is it equal to? Yes, work done or crack is stationary, it's not propagating. Therefore, if the crack is static, it's not moving. Let's say that. I mean, for a given crack length, in other words, strain energy is equal to work done. Yes. And the body is deformed. Yes. It's being deformed. That's right. And for a given crack length, that's right. That's deformed shape. The deformed shape is going to be formed like this. And for a given crack length A, what is strain energy stored? I know for a given crack length, that's 1/2 times V. That's equal to work done. And I can evaluate now considering the variation of this. I can calculate the energy release rate by considering different loading cases. For example, as case 1, assume that F stays constant during crack propagation. You increase F at a certain value, crack starts to propagate. Not I apply force control and I keep force constant during propagation of the crack. That's simply referred to as constant force loading. Also referred to as constant force loading. And I can evaluate or end up with an expression for energy release rates under these conditions. Now, the starting point, what's energy release rate? It's DDA W minus UE. That's a starting point. However, I will replace this derivative. It is dA. I'm going to write it in terms of crack length. Using chain rule, you can write this as dd lowercase a dA. You can write it in this form. And we know that A equals A times B. And therefore, the ADA is, what is it equal to? What is the ADA? Yes, that's right, it's 1/V. And the right derivatives of results in terms of crack length, DDA is 1/B DDA, and energy release rate is 1/B DDAW minus UE. And I can express the work at energy terms under this condition. For example, total work done on the specimen is work done by these forces. Therefore, you can rewrite this as FdV, total work done on the specimen. That's differential work. And change in strain energy of the specimen can be calculated in DUE, and it's going to follow from this result, DUE. We are going to use this result that is under constant force. This DUE is 1/2 dFV plus 1/2 FdV, right? But dF is 0. Therefore, it will be 1/2 FdV. Force is constant. And it's going to be written like this. And this will lead to the differential quantity, the W minus UE, is 1/2 FdV. The difference is also 1/2 FdV. So the difference between work done and change in strain energy is the energy available for fracturing the specimen. And now you can divide this by dA, this quantity, and it's going to give you G as F/2V dV dA. And I'm going to place a subscript here, a subscript F, which indicates that this is constant force. Result. And release rate, one of the results we will use is obtained in this form. I can rewrite this if we consider strain energy or recall strain energy for a given crack length. This is equivalent to, can be written as, this is actually DUE dA under constant force conditions. As you can rewrite it as 1/B DUE dA under constant force conditions. And this is the second result related to this computation. Energy this way. Now we don't have really that much time, but it's possible to derive these results graphically. Or you can consider a graphical interpretation of these results. Now I can show this on a diagram, say that we are dealing with an F versus V diagram like this. When I increase the force, it's going to be the relation between F and V. Now I suppose that crack propagation started, but now that we have a control on force and we are keeping it as constant for this crack propagation direction. And at the end or in the next stage, there is going to be a new crack length and lower stiffness in the specimen, so that at this initial point, crack length is A, and at the final configuration, crack length is A plus delta A. And there's a certain amount of delta V here in the specimen. And I'm going to label these points as O, A, B, C, and D. This crack propagation direction. If you recall the original results for energy release rate, G is 1 over B, DDA W minus UE, is that right? The difference between these energy terms is available for fracturing the specimen. In terms of the limit definition of derivative, you can write this, or the method of increments, the basic method. I can write this derivative as limit delta A goes to 0, delta W minus delta UE over delta A. I'm going to show these energy terms as areas. Work done by the force during crack propagation. Well, which area is equivalent to this? Work done by the force. This area, A, B, C, D, that is the crack propagation region, force is constant. Now, the area below that line is area of this rectangle, A, B, C, D. And change in strain energy of the specimen. Final strain energy minus initial strain energy. Final strain energy is OBD. Area OBD, this triangle. Initial strain energy, OAC. Area OAC. But we are looking into this difference, delta W minus delta UE. This is the energy available for fracturing the specimen. What's this area? Delta W minus delta UE. Area ABCD plus area OAC minus area OBD. Which area is this? That's right, this area. That's correct. This is the difference. This is referred to as energy available for fracture. And now this is replaced by area of OAB, this triangle. And in the limit, okay, we are at the end anyway. In the limit, G is 1 over B 1 over b, limit delta A goes to 0, area of OAB over delta A, and area of OAB can be written by considering the area of this triangle, which is 1 over 2 base times height, is 1 over 2 f times delta V. And if you substitute and evaluate the limits, you will get then G becomes f over 2b dV evaluated by considering constant force condition. For any given crack length, this is the energy available for fracture. It can be evaluated by a general expression. It's given as a general expression. And an approximation is used in fracture tests as an approximate result. Can use this. You see, we have the limit here, but area over B delta A. Area of OAB divided by B delta A can be used if there is available data in fracture tests. Now this is, as you see this in this diagram, crack length is changing from A to A plus delta A. And once the amount of energy available for crack propagation is this area, and if it can counter the resistance of the material for crack propagation against crack propagation, the crack will extend and crack propagation is going to occur. Therefore, this is the fracture criteria, and this is the basis of stress intensity factor criterion as well. As a result, we have considered a certain loading case, constant force. We'll look into constant displacement loading as well. But we have any comments or questions regarding these results? If you don't have any questions, we will continue with this next week.